So good evening, students. We have been discussing, I think, about the approximate method, how to obtain the eigenvalue, eigenvector. Some of the methods which we were familiar with regarding the Rayleigh's quotient and the enclosure theorem. So that thing we are now extending it for obtaining not only the fundamental frequency, but also more number of frequency depending upon the requirement. So in the last class, we discussed Rayleigh-Ritz method, in which the functions which we were choosing, the comparison function. Earlier, we used to choose a single function, but in the Rayleigh-Ritz method, we choose such functions in series form, and these are associated with some constant coefficients. And we started with the minimization of the Rayleigh's quotient with respect to these coefficients, and we found that we formulated an eigenvalue problem. So we started with the continuous system, but we formulated eigenvalue problem similar to the discrete system. So that means basically we discretize the continuous system using this form of solution to n degree of freedom system, and this n can be any number depending upon the accuracy desired, and in a limit when we have n tends to infinity, we expect that this particular solution, eigenvalue problem solution, will give us similar results as the continuous system. But as a when we are talking about discrete system, so we have limitations. We cannot have the infinite degree of freedom system. We need to truncate at some number, and also, as we know, that the first few natural frequencies are important because they are the frequency which can get into resonance, and the prediction of these natural frequencies are important rather than all the infinite number of natural frequency. And especially when we are talking about higher frequency, then even the response of such systems will become nonlinear, and so even we can able to get those very high natural frequency, but the theory, the linear theory which we are discussing, may not be valid at that point of time. So now I will discuss regarding the Rayleigh-Ritz method. We already discussed, so we were in the last part of that, and we'll see, because as what we do, we approximate the continuous system to discrete system. So always the problem of the computation comes. So people try to reduce the computation by some method. So that also we'll cover today, and then we'll take up some example. So I'll share the screen. So we were in this particular slide in the previous class. We obtained, when we minimize the Rayleigh's quotient, we obtain the equation something like this, where these coefficients we defined earlier like this, Kij and Mij. These are the coefficients we got it in the Rayleigh-Ritz method, and finally we can able to convert that simultaneous equations in the matrix form, or like this. So this is a standard eigenvalue problem, but you'll see that there is some difference. Here, anyway, we have K matrix, M matrix, Usually we have a generalized coordinate here, but now this A matrix contain the coefficients which which are unknown to us, and this is the comparison function. So the eigenfunction, approximate eigenfunction, is represented in the series form using the comparison function. Main difference, and because here we started with the continuous system and we got the equivalent discrete system eigenvalue problem. So as in the continuous system, we had the eigenvalue problem as the ordinary differential equation, but now because we have discretized the continuous system, so we have eigenvalue problem using the Rayleigh-Ritz method is similar to the discrete system, that is simultaneous homogeneous equations. Here usually we used to write the lambda eigenvalue, but here because this is approximate, so we are representing inverted V, and n is representing that this is n degree of freedom system we have approximated. So when we write inverted V R n, so R is the rth eigenvalue, and generally, as I mentioned, if because this is a we have equivalent multi-degree of freedom system, so we'll get n number of eigenvalue. So because in the approximate method Rayleigh's quotient, we know that eigenvalues either over predict the actual eigenvalue, or that will be at the most equal to that. Either it will be more than the actual value or equal to that. Equal to that when we have the same eigenfunction as the actual one. And but this comparison functions which we are choosing is approximate, so always we expect that the eigenvalue which will be getting approximate eigenvalue will be more than the actual eigenvalue. So we are always getting the upper bound of the two eigenvalues using the Rayleigh-Ritz method. Now, once we have obtained the eigenvectors also corresponding to these eigenvalue, so eigenvector will correspond to these coefficients. So those coefficients for each mode we need to substitute in this expression, and that will give us the eigenfunction, approximate eigenfunction. So these coefficients will be that will be found from the eigenvector. So this is the key. So through example, I think this will be more clear. So eigenfunction, approximate eigenfunction is this, which will give us the actual shape of the system, beam, or the whatever the system we are considering. The shape actually will be this, which is given as series form like this. This was the starting point of our solution. Now, as I mentioned, what we do in the Rayleigh-Ritz method, because we need to find out, let us say if you want to find out few natural frequencies of the system with some accuracy, desired accuracy. So what we'll do, we'll take first only one comparison function. If we have one comparison function, then this is same as the Rayleigh's quotient, because only one coefficient is there, we cannot able to minimize that. Only one is there. So, but when we are two, so we can able to minimize using the Rayleigh-Ritz method, and then next maybe we can take 3, 4 like that, and we'll watch for a particular eigenvalue, which particular eigenvalue is not improving further. So that means if some eigenvalue is not improving further, that means the accuracy of that has been achieved up to the desired decimal point. So this is the way we generally increase the number of terms in the approximate eigenfunction by choosing more and more comparison function. And as I mentioned, that if we are adding the more terms, that means because in actual case the degree of freedom is infinity. So when we are adding more term, we are relaxing one constraint. So once we are relaxing one constraint, so we are going more closer to the actual eigenvalue. So in a limit, when we have this terms as n tends to infinity, this Rayleigh's quotient will give us the approximate eigenvalue will converge to the actual eigenvalue. So this is the limit. Okay, but for practical purpose, because we cannot have infinity, but we'll go as high as the n number so that we have the eigenvalue up to the desired accuracy. Okay. The main problem here in the Rayleigh-Ritz method is the choice of this comparison functions. So that is the main criticism of this method key, how to choose the comparison function, because sometimes is quite difficult. But through some experience, I think it can be chosen conveniently. And sometimes this choice of this function, the comparison function, is or taken from the eigenfunction with some slightly different configuration. So like if we have a cantilever beam with some other spring and a disk attached at the free end, then we can take some information regarding the eigenfunction without those complexity. So that will give some information regarding choice of this function. Comparison function. Then, because we are choosing different eigenfunctions, they may not be orthogonal to each other. So there are some functions which are orthogonal to each other, like trigonometric functions, Bessel's functions, legendary polynomial, etc. Once they are orthogonal, then we have the complexity of the computation reduces because they are orthogonal to each other. So whenever there is a cross product in the integrations, those terms will be zero. So we have so often this kind of functions also people use it, but there is another way by which we can able to convert the chosen comparison function to orthogonal by some generic procedure. So that I am now describing. So there is a more to do with the reducing the computational time. So let us say u1, u2, u3. These are the comparison functions which are not orthogonal to each other. Orthogonal to not to each other means we already the orthogonality conditions, so they are not satisfying those conditions. So we are defining a new set of comparison function vi, which are the same number as the ui, and we are defining the v1 like this. So v1 is equal to u1, but u2 is equal to a12 v1 plus u2. So a12 is a constant. v1 is we already know from the previous step. u2 is the comparison function initially which we had chosen. Similarly, v3 is a13 v1, a23 v2 plus u3. So here a are constant to be found out such that v1, v2, v3 they are orthogonal to each other. Similarly, vn. So in vn we have so many other unknowns. So basically the aim is to get the orthogonal functions from the comparison functions which we have chosen, which are satisfying the boundary conditions. Okay, so even we will be getting, because often we normalize with respect to mass. So if we define this so that they are normalized with respect to mass also, then that will be orthonormal in generalized sense they will be represented. So let us see how this constant can be found out so that we get V1, V2, V3 in the form of orthonormal form. So we know that this V1 M operator, V2 D. So if V1 and V2 are two distinct eigenfunctions or the comparison functions, then what we expect to satisfy the orthogonality condition, if they are different, it should be 0. So this should be 0. But now let us see if we substitute the V2 here from here. So V1 is as it is, M operator, and V2 is this A12 V1 plus U2. And then we expanded this. M operator is a linear operator, so this can come inside. So we'll get two terms from this. First is A12 integration V1 M V1 D, capital D, and then the second term V1 M U2 D, capital D, and that is equal to 0. So now if you see, this equation can be solved for A12, which is unknown to us. So if we solve this for A12, we will get this is minus this integration, because this was the previous expression divided by this expression. Now in the denominator, if you see V1 M V1 and the integration is there. So if we want to normalize this with respect to mass, the new orthonormal function, then this quantity should be 1. If this is 1, that means the whatever we are getting function, they will be not only orthogonal but also the orthonormal also. So if this is 1, then A12 will be this quantity, because V1 we know that is equal to U1 and MU2. U2 also we know, so we can able to obtain the A12. So in the previous thing, we could able to get the A12. That means now we know V1 and V2 also in terms of U1, U2. Now we want to find out the V3. It contains two unknowns. So we write like this: V1 M V3. So instead of V3, then we put the expanded form of that, A13 V1 plus A23 V2 and U3. A13 and A23 are unknown. Now we operate the M operator. This is a linear operator, so we'll get A13 outside the integral, and then V1 M V1 D, the integration with respect to the domain. A23 outside, then this integration, and here last term is V1 M U3 this. Now if you see the first term, the integration, only the integration part, V1 M V1. So this already we know that is normalized, so this should be 1. So here we left with A12, A13. Here V1 and V2, because earlier we already obtained V2, which is orthonormal to V1. So according to the orthogonality condition, they will be 0. So the whole term will go. Only unknown will be here A13. So A13 will be negative of this, negative of V1 M U3 this. So in the V3, we could able to get the A13, but still A23 is unknown. So for that, now we'll take integration V2 and V3. So initially we did V1 and V3. Now we are using the V2 and V3. So here V3 again will need to substitute like this and then expand. So we'll get 3 terms similar to the previous one. Here the A13, V2 and V1 is there. And according to orthogonality condition, this will be 0 because they are different functions. Here in the second term, A23, here V2 is there. So according to the orthogonality condition, they will be 1, or the normalization condition, it will be 1. And yeah, so only thing is A23 is left out, so that will be minus of this. So we got the A23 also on the V3. So we got this also, this also. So we got V3 also. Now let us see what are the coefficients we obtain. We obtain A12, what is the form of that? Minus V1 M V U2. A13 minus V1 U3. A23 minus U2 M U3. So there is some cyclic change. You can see the first subscript is V1, second subscript is U2. So the same trend is there. So if you do more and more terms, you'll get the same trend. So that means if these coefficients we define as RS, R can take value from 1 to n minus 1 and this. So this will be defined as VR M operated on US, the second subscript. So the coefficients directly we can able to get from here. So with this, we have got now all the coefficients of these. So even and V1 to Vn we could able to get. They are now orthonormal functions which are easier to integrate as compared to the which are not orthogonal. So yeah, in this particular case, what will happen? I think this should be yeah. So here this should be omega square because we are normalized with respect to mass. So here identity matrix will come. So here I think it should be omega square will be better. And this will be diagonal because now we are normalize this. I hope I'm correct. Okay, but this will be identity matrix, mass matrix. This can be fully populated also, but I think this will be diagonal now. So now another procedure by which we can have the reduction in the computation. If the system is having certain symmetry, the system means the beam or whatever the problem we are solving, if it is having some symmetry, then the computational work can be reduced by this procedure. So let us say we have one-dimensional problem like beam or other things in which we have the following properties are available. So we are talking about symmetry about the midpoint of that particular system. That means from minus L by 2 to L by 2. So in this particular case, we need to define the origin at the center of that particular system. So if we choose the comparison function, which is even function, the choice of the comparison function is even function. That means ui x is equal to ui minus x. So if we put in place of x minus x, then also if we get the same value of that function, that is a even function, then the L operator onto that particular comparison function also will be equal to L operator on the minus of that particular eigenfunction. Similarly, M operator. So if the function which we have chosen, the eigenfunction, the comparison function, is the even function, then the L operator will be have this property. On the other hand, if the comparison function is odd function, that means if we substitute in place of minus x, the quantity from the comparison function will be minus. So ui x is equal to minus of the ui minus x. So here in the previous case, because it was even function like x square. So x square, if you put minus x, that becomes x square only. But if it is x cube, then that becomes minus of x cube. So that is the odd function x cube. So then the operator, L operator and the M operator also will change the sign if we apply the comparison function minus of that. So when we have this thing that if we have either both, here if you see the when we calculate the Kij in the Rayleigh-Ritz method, Kij is defined as ui L uj. So if u and j, which two functions which are there, if both are even function, this is the definition of the even function, or if both are odd function, ui is also odd function, uj is also odd function, or both ui and uj are even function. If that is the case, then the integration of Kij, which generally we do from minus L by 2 to L by 2, because of symmetry, we can just do the half of the integration and twice of that will be the Kij coefficient. So Kij coefficient is what? That is the stiffness matrix coefficients, because to discretize the continuous system to discrete system, we need to evaluate these coefficients so that we can have the stiffness matrix and the mass matrix. So this is fine when both are even or both are odd, then they are twice of that, half of the integration. But if like ui is even function and uj is odd function, or other way around, ui is odd function and uj is even function, then this coefficients will be 0 for that particular case. So if we are calculating the Kij or Mij, if the corresponding eigenfunctions are one is odd and another is even, then those coefficients will be 0 directly. There's no need to calculate them. So this is some computational trick by which we can able to reduce the computational time. Also, if we have, let us say, out of n number of comparison functions which we have chosen, if let us say first r eigenfunctions are even function and remaining n minus r functions are odd function, then we'll find that because Kij corresponding to their cross products are 0, so we will get the eigenvalue problem like this, in which the odd, the even function, the coefficients will be this is the odd coefficient corresponding to the comparison function. So cross products are 0, so these will be 0. If all are odd or all are even, then this K matrix will be fully populated. But here we have segregated it, and because some of them are even function and remaining is odd function, So their corresponding cross products, as we have seen here, are 0. So we will be getting the eigenvalue problem like this. And if you see, this can be split in two eigenvalue problem, one for the even functions, another for the odd function. So here the eigenvalue problem order will reduce to half. We'll be solving two eigenvalue problem, but the size of the matrices will be higher. That will be half. So that is the advantage of this. So when we have large computation, then these methods are very useful. Okay, so I'll take up one example now. Just take. So so we have a simply supported beam. This is very important. This showing that is having transverse vibration. This is a transverse vibration, bending vibration. This I have shown representative beam, but actually the beam mass is varying like this. Stiffness is also varying like this. So the beam is non-uniform, and the shape of the distribution of the mass per unit length is given like this and another like this, where L is the length of the beam, X is the coordinate from one end to another end. We are using the Rayleigh-Ritz method, and here our aim is to obtain not only the single natural frequency but also the two natural frequency of the system. So initially I will try with the single comparison function, then I will take 2, even we can take 3, 4 like that gradually and see how much improvement in the natural frequencies are taking place. So these are the given information in the problem, the mass distribution and the elasticity distribution. And for beam case, the L operator and M operators are given like this. So beam case, we have L operator as fourth order differentiation. So we should be taking this. The boundary condition of that, we know that because there is a pin joint at the both end. So at x is equal to 0, we have displacement 0. Also the bending moment is 0. So that is representing the bending moment. And then at other end, x is equal to L, we have displacement 0 and the bending moment 0 at x is equal to L. Now the first case, we are taking the comparison function, only single one. So this is the one comparison function. So this has been obtained by trial. It's not something systematic method is there. So if you see this comparison function, we will see whether they satisfy the boundary conditions or not. Because Rayleigh-Ritz method, when we use the comparison function, they should satisfy not only the geometrical boundary condition of the problem, but also the natural boundary condition of the problem. So let us see first the satisfaction of the boundary condition, whether this satisfies or not. So because it involves derivative up to 2, so if we derivate this once, we'll get this. Twice, if we differentiate, we'll get this. Now, if you see the boundary condition, this one at x is equal to 0, x is equal to 0, this term is 0. So it's satisfying the boundary condition of this. Second boundary condition, at x is equal to L, L should be 0. That means if we put x is equal to L here, whether this becomes 0 or not. So if you see, this is L raised to 4, if you put x is equal to L, this will be L raised to 4 by 6 and plus L raised to 4 by 12. So this will become 0. So this also will be satisfying by this equation. Then this second boundary condition. So using this we can able to check, because this is a second derivative. If you put x is equal to 0, because x is in the common, so this will be 0. So this is getting satisfied. And second one, when x is equal to L, the second term will be 0. So this is also satisfying this boundary condition. So now you can see whatever the comparison function we have chosen is satisfying all the boundary condition of the problem, natural boundary condition and the geometrical boundary condition. So that is a must in the Rayleigh-Ritz method. For cantilever beam, the comparison function will be different. For fixed beam, comparison function will be different. So different boundary conditions will be having different comparison functions. So this is only for the simply supported beam. Now let us see the Rayleigh-Ritz method. Rayleigh-Ritz method requires the finding the coefficients. So if you see here, K11 is defined as U1 L U1 dx. So we'll be doing this operation step by step. So because L operator we know is this. Here first we'll do because here we require the LU1 operation. So LU1. So L operator is this U1. U1 is nothing but the comparison function which we have chosen. So if we substitute that here, this is the comparison function. Now we need to operate this differentiation. So if you operate this differentiation, we'll get this. Now EI is varying with respect to x as given in the problem. So that also we need to substitute. So EI we need to substitute. So EI is this function from here to here, and the derivative which we have taken is this. So now we could able to introduce the EI variation here. Now we need to multiply this and then differentiate and simplify. So this will be long differentiation, so that after simplification, L operated on U will be this function. So we got the LU1. Now we need to substitute in this. So here you can see U1 is the comparison function chosen. LU1 we obtained here, so that we are substituted. Now we need to multiply this and then integrate. So you can see that a lot of multiplication integrations are involved, but because these are polynomials, so they are easy to integrate as compared to other functions. So if you do these operations, then we'll get simplified K11 like this. So now you can see that the integrations are involved much. So that's why in the previous slides I have shown how to minimize the integrations by if the system is symmetric, or by using the ortho normal functions. That kind of tricks we was explaining. But in this example, we have not done the orthonormal thing. So this is the stiffness K1 we obtained. Now the mass coefficient. Mass coefficient is given like this: U1, M operated on U1 and integrated over 0 to L. Now here is important to see that because M is just operator Mx. So when we are operating M on U1, we'll get Mx as it is and U1. So when we operated the M on U, so U1, Mx, U1. So basically what we got, Mx, U1 square. Mx variation we know is given in the problem. That is, this is the variation of that with m by 3. So this is the mx variation because mass of the beam is varying with the length, and this is the comparison function u1 square of that, u1 square. So here also you can see this, you need to expand this, then multiply with this, then integrate, and if you do this, you'll get something like this m11. Now here we used a single comparison function. So the Rayleigh-Ritz method is same as the Rayleigh's method. So that means K11 divided by M11 square root will give the first natural frequency. Here the superscript 1 is representing that we have used only the single comparison function. So if we substitute the K11 and M11 here and simplify, we'll get the natural frequency like this. So this is the same as the Rayleigh-Ritz method. There's no change. So because single comparison function is there, so there is no other terms, and only the one natural frequency, the lowest natural frequency, will be getting from this. So corresponding the mode shape or the eigenfunction. So that will be this, whatever the comparison function we have chosen will be the mode shape, because there is only one constant involved, and that can be normalized. So A1 is anyway we can not able to obtain in absolute way. So and only one value is there, so there is no ratio of that is involved here. So this will be the eigenfunction directly. So we can able to plot the corresponding mode shape using this. Now when we take the another eigenfunction or comparison function. So now we are taking two number of comparison function. One already which we have chosen u1, another we are choosing is u2. Now u2 is this one having fourth degree polynomial, and we need to check whether they are satisfying the geometrical boundary condition and the natural boundary condition or not. So we can differentiate this twice, and you can able to check that at x is equal to L, x is equal to 0, this is becoming 0. At x is equal to L, this also will check, there will be 0. And at x, the x is equal to 0 and x is equal to L for the bending moment also, this will be 0. This on the same line as I have checked for the u1, for u2 also you can able to check and find. You can find that it will satisfy both the natural boundary condition and the geometrical boundary condition of both ends of the beam. So that is, we have chosen two comparison function. Now we need to obtain the K22, K12, K21 will be same as K12 because of symmetry. So here in this slide, K22 has been shown how it can be obtained. So K22 will be integration of U2L or U2 dx. So now this particular LU2 we are obtaining here. So this is the L operator and U2. Now if we put the U2 here, we get this, and now we can operate, we can substitute the variation of the EX also, but before that if we differentiate this twice, we'll get this. So variation of EI also there, so that can be substituted, and the differentiation of this. So now we need to multiply, then differentiate twice of that. So then we'll get the this LU2 like this. So and this then we need to substitute here and multiply by the U2. So this is U2 and this is the LU2 from here, and then again we need to multiply and then integrate 0 to L to get K22. So this is a long process, but for simple functions, polynomial, this can be done with some patience. So K22 we obtained. Now K12. K12 is the one U1 L U2. So here we already obtained LU2 earlier. U1 we know, so it is U1. LU2 we can substitute from the previous slide. Then multiply and integrate. We'll get the K12 like this. K21 also will be same. K21 will be nothing but U2 L operated on U1. So that you can able to see that they will be same as the K14. So we obtain the K11, K12, K22 and K21. So all four the stiffness coefficient we obtain, because when we are using the two comparison function, we are discretizing the continuous system to 2 degree of freedom system. So the matrix, stiffness matrix will be 2 by 2. Similarly, we can able to obtain the mass matrix M22 by using U2 MU2. So this will be MX is this, and U2 square is this. If we integrate, we'll get this. Similarly, M12. So M12. So here again, we need to put the variation of the mass and the square. Here U1 and U2 is there. So this is U1 and U2. And if you integrate, we'll get the. So here also M12 and M21 will be same. So now we got all the matrices elements. So mass matrix we obtain. This is M11, M12, M21, M22. Similarly here K11, K12, K21, K22. So this is the coefficients in the previous slides we obtained of the mass matrix and stiffness matrix. Now once we have this, the eigenvalue problem we can able to solve same as the we have been doing in the chapter 4. So that I'm not showing the steps how to obtain the eigenvalue for 2 by 2 matrix. We already familiar with that. So I'm giving just the results. So the first natural frequency of this will be, because we'll get two natural frequency and two eigenvectors. So first will be this 9.8 this, and corresponding eigenvector is this 1 and 0. So eigenvector is the coefficients. So now you can see this is the natural frequency, and the eigenfunction, the mode shape will be given as W, A1 U1, A2 U2. So here the eigenvector is 1 and 0. So they are not the shape of the actual system. We need to substitute the coefficient A1 here and A2 here. A1 is 1, A2 is 0. So U2 will not contribute in the first eigenfunction. Only the U1 will contribute, and that is this. Similarly, the second natural frequency from this eigenvalue problem will get this. Eigenvector corresponding to that is 1 minus 0.5 L and 1. Corresponding to the second natural frequency, the mode shape is U2, A1, U1, A2. So A1 and A2 we need to substitute from here. So A1 is 0.5 L minus 0.5 L minus 0.5 L. This is U1. A2 is 1. A2 is 1 here. And this is the U2. So this is the eigenfunction for the second mode shape. So I have plotted this also, how they will look like in the subsequent slide. So now you can see that we, by choosing two comparison function, we reduce the system to two equivalent degree of freedom system. We got two natural frequency corresponding mode shapes with the help of comparison functions. These are the plot of the mode shape which we obtained in the previous slide. So W1 we had this function. So if we plot the mode shape from 0 to L for the first mode, this will be like this. If we plot this, we'll get this. For the second, we got the eigenfunction like this. If we plot this, we will get the mode shape like this. So we are familiar with this kind of mode shape or simply supported beam, that the first mode is something like half sine and this is like full sine, but we are obtaining that from the approximate polynomials or the comparison functions. So that is the difference here, but we could able to get the complete solution of this using the 2-degree of freedom system. If we take 3 eigen comparison function, then we can able to get the 3 natural frequencies, 3 eigenfunctions. There the we'll be having a1, a2, a3 as eigenvector. So here also we'll be having one term. So we can able to, only thing I have not shown the 3 because the procedure I wanted to explain here, that can be done for 3 also. More computations will be required for that. I'll just take one more minute. This is a code I have written. In this, if you see, this symbolically, it is doing the differentiation and integrations. So whatever the shown for the n is equal to 1, only for u1, this the code is there, but this can be extended for the n is equal to 2 or 3 also. So here you can see this is symbolic representation of the x, m, l, ei. This is the distribution of the mass, which is given to us. Distribution of the elasticity, which is given to us. Comparison function, we have chosen u1. As I said, I have taken only the one function here, but this code can be extended for 2 functions. So u1 is the first comparison function. This represents the differentiation of the first comparison function with respect to x twice, because bending moment requires the 2 times differentiation. So it will do the symbolic differentiation of this. And then LU1 we obtain by differentiating the EI variation and the this U1 variation or differentiation. So this is the L when applied to U1. This is the expression is there. So now you can see that directly we can able to get U1 by this expression in the symbolic form. And then the K1 also can be, we can get by integrating it. So here I have integrated U1, LU1 with respect to X from 0 to L. So this will give directly as the K11 coefficient. Similarly, I have done for M11 coefficient. And then if we take the square root of that, I can get the natural frequency, first natural frequency. If we want to do K12, just we need to replace this U2 and LU1. If we want K22, we can define U2 here and then we can say U2, LU2. So this can be extended for this 2 case or 3 case also. And this is the output. You can see the distribution of the mass, the elasticity, U1 we have defined. If we differentiate, we get this twice of this LU1, this expression. If we I think simplify this, there is a command, I think pretty simplify. So this gives the simplified version of the LU1, K11 directly from this, then MU1 and M11 and the natural frequency. So this is the code which you can able to use for your assignment if you feel like. If you want to do an integration differentiation, you are welcome to do that also. So this is, I'm stopping here. If you have any query regarding this, you can ask me. Any query on the today's lecture? Because now these are approximate methods, and for 3-degree, 4-degree problems. This involves very large computations. Especially now you can see that we have analyzed a beam having uniform mass distribution, non-uniform mass distribution, and the elastic distribution. Theoretically, using an eigenvalue problem formulation, that is very difficult, but with approximate method, at least we are getting those relatively easier without solving the differential equations. So if you have any questions, please. So on Monday we have a quiz, the second quiz based on the continuous system, and only the Rayleigh-Ritz method, Rayleigh's quotient and the enclosure theorem, which is there in the chapter 5. The approximate methods, which the chapter 6 is not there, only the chapter 5. And so whatever I covered in the class, I have not covered the two-dimensional problem at present, and that is not there in the quiz. Okay, then, so